Welcome back. In today's lecture, again we begin with general second order equation with two different speeds. Last time we started that, and we derived this formula for the solution of the second order equation with two different speeds C1 and C2. So, it generalizes the D'Alembert's formula, known D'Alembert's formula. Of course, when we take the C2 equal to minus C1 equal to minus C, this reduces to D'Alembert's formula. And now we ask the question, what happens if C1 equal to C2? Okay. So, before coming to that, so let me just mention one more important property of the wave equation. So, this is called characteristic parallelogram property, which we are going to use later. In fact, this property characterizes the wave equation, as we shall see. Characteristic parallelogram property. For short, I will use the CPP to denote this. Okay, so CPP. So, again we consider the wave equation. So, here the initial conditions are not explicitly used, but they are in the background. So, this is the wave equation. Now, you consider a parallelogram, not any parallelogram, but a specific one. So, here I denote this A, B, C, D. So, the sides of the parallelogram A, B, C, D are line segments of the characteristics. So, that is why it is called characteristic parallelogram. Okay. Then the important property CPP states that U of A plus U of C equal to U of B plus U of D. So, you consider any solution of the wave equation and then you evaluate the solution at the opposite vertices A and C and B and D, then you add them. So, this is sum of these solutions at A and C, and this is sum of the solutions at B and D, and the characteristic parallelogram property states that U A plus U C is equal to ub plus ud. So, if you know the values of the solution at 3 points, any 3 points of the characteristic parallelogram, then the value at the 4th point is determined by this property. So, this is an important property which we are going to use later. So, conversely, if that is the characterization, conversely if u is any C2 function. So, I am not necessarily, I am not referring to solution of the wave equation. If conversely, if u is any C2 function satisfying CPP for all characteristic parallelograms, then u satisfy the wave equation. So, that is the characterization. So, we are going to use it later. So, again back to this second order equation with only one real characteristic. Okay. So, this equation, so this equation I will write del t minus c del x square u equal to 0. So, homogeneous equation I am considering. So, there is only one real characteristic, but this should not be called as parabolic. So, the equation del t minus c del x square u equal to 0 is classified as weakly hyperbolic. So, perhaps you are first time hearing this class of equations. I will give you two reasons why this equation should not be classified as parabolic. So, the first reason is, so consider the characteristic variable. So, there is only one characteristic. So, j is equal to x plus c t, and now we choose another variable, so that the change of variables is again non singular. So, Jacobian should not be 0. So, the easiest choice is x minus c t. Okay. But remember, this time this is not a characteristic variable. So, we are choosing a different variable, so that this x t change of variable to j tau is non singular. So, we are assuming of course C naught 0. If C is 0, then the equation reduces to a ODE. Okay. So, it is not even a PD. Okay. So, again you do the computation. So, you see that the equation implies, so some computation, you show that del tau square u is 0. So, in these new variables you show that the del tau square u is equal to 0, okay, and this does not resemble the heat equation. So, this is more like a ODE because it is only del tau square. So, there is no del J there. So, it is more like an ODE. So, far from the heat equation. Heat equation, which is a typical example of parabolic equation. Okay. So, this is one reason why this equation should not be called as parabolic. The another reason, to solve this equation, we need two initial conditions. Whereas, heat equation requires only one initial condition. So, for these two reasons, again I stress that this equation should not be classified as parabolic. So, it is classified as weakly hyperbolic. Now, let us quickly solve the initial value problem or Cauchy problem associated with this equation. So, since there are this C repeats here, so such we can call this double characteristic equation. So, if the multiplicity of the this characteristic is more than 1, so you generally it is called multiple characteristic, and in this case since there is only repeats twice, so it is a double characteristic equation. Okay. These are more difficult than the, in contrast, the equation. So, let me show you that. This equation is called equation with simple characteristics. So, we are assuming C1 is different from C2. So, this there are two real and distinct characteristics here. So, this is called simple characteristics. Okay, now, let us quickly consider the initial value problem or Cauchy problem. Of this double characteristic equation. So, del T minus C del x square equal to 0. As I said, it requires two initial conditions. In case of wave equation, we required u0 to be a C2 function and u1 to be a C1 function, and let us see what difference we will observe here. Okay. So, for the time being, assume u0 and u1 are such that we can obtain a C2 solution of the equation. Okay. So, now since there is only one characteristic, so we already done it here. Let us go back. So, we get this with this change of variable in the new variable j and tau, this equation reduces to del tau square u equal to 0. Okay. So, that we can immediately integrate and obtain the solution. Okay. So, this implies del tau square. So, let me not repeat again. Okay. So, which again in turn implies u of, remember u is a function of j and tau. Okay. So, this is a linear function in tau. So, we can write this as, so the constants can be functions of j. So, this is the general solution of this equation. Okay. So, let us go back to the original variables. So, general solution u x t. So, now again I write in terms of the original variables x and t. Okay. So, this f 1 x plus c t so tau is x minus c t, f 2 x plus c t. So, we can arrange the term little bit and write it in a neat form. Okay. So, we write x minus c t as x plus c t minus 2 c t, and you absorb this x plus c t term in this function, and so we have only a multiplication by t. So, general solution we can write it as, one more time I will write it. So, u x t, so let me use different notation, x plus c t plus t f 2 x plus c t. So, you can easily verify that the expression given by this for u satisfy the given equation. This is the equation. And now, in order to determine f 1 f 2, again just recall what we did in the case of wave equation to arrive at D'Alembert's formula. So, I leave it as an easy exercise. So, you plug in the initial conditions in this general form, and finally, you obtain the solution. So, I am skipping few steps, can easily find them and work out x plus c t minus c t u 0 prime. So, this is derivative of u 0 plus t u 1 x plus c t. So, if you compare this form of the solution with the D'Alembert's formula, you see a big change here. First of all, in the D'Alembert's formula, no derivative of the initial conditions appeared, but here the derivative of the initial condition appears. There is no integration of u 1, but u 1 appears as it is. So, now we require, so for u to be a C 2 function, and that is what we need, at least 2 derivatives, u to be a C 2 function of x and t. We require u0 to be a C3 function, because there is already one derivative in the formula of the solution. So, if we want u to be C2, so this has to be C3, and similarly u1 has to be C2. Okay. So, we require more smoothness in the initial values to obtain a less smooth, see u0 is C3, but that gives u only a C2 function. So, this is referred to as loss of regularity, and this is typical of weakly hyperbolic equations and systems, loss of regularity. So, more smoothness of the initial values required. Okay. So, but now we can simply combine the two cases. So, let me just mention as a general remark. So, equations of higher order. Okay. So, this is just follows from an induction argument. So, first consider equation with simple characteristics. So, the operator L, I write it. So, this is C1 del x So, a kth order differential operator which can be factored into linear factors. So, that is the form of the higher order equation, okay, where C1, C2 all distinct real numbers. So, we did for it the case of two values. So, but the same procedure reals. So, what we can show is this general solution now. So, this is just followed by an induction argument. So, I will not do the details, you can do it yourself. General solution of LU is equal to 0 is given by u of x t is equal to f1 x plus c1 t plus etcetera. CKT, where f1, f2, fk are k times differentiable. Okay. So, here it is important that they are all distinct, otherwise you will not get this one. Okay. Of course, in order to determine this f1, f2, fk, we have to prescribe k initial conditions on the solution, but it is more algebra. You have to solve a k by k linear system, but in principle it can be done. Okay. So, what about so that is with simple characteristics. So, let me just, so this is simple characteristics. What about multiple characteristics? So, it's similar thing. So, so this is the equation del x k u equal to 0. So, k is bigger than 1. Earlier we did for k equal to 2. So, again by an induction argument, the general solution is given by u of x t is equal to f 1 of x plus c t plus t. This we saw for k equal to 2, and now you do an induction argument and you get this. And you see this factor t, which was not there in D'Alembert's formula and even in this simple characteristic problem. See, even in simple characteristic problem there is no t factor at all, but when you go to multiple characteristics, so you see this factor of t. Okay. So, now we can combine these two simple characteristic equation and multiple characteristic equation into a single one. So, a more general equation, general operator. So, L is equal to L 1 L k. So, L k is this operator L j, let me use L j. C j del x, I put n j. Okay. So, j equal to 1 to k and C 1, C 2, C k are real and distinct. So, if n j equal to 1 for all j, then we have simple characteristics. So, that leads to simple characteristics. And if n j is bigger than 1 for some j, even for one j, it is multiple characteristic problem. Okay. So, the general solution of LU equal to 0 is given by U is equal to U1 plus U2 plus UK, where LJ Uj is 0. And this we have now learned how to solve that equation. Okay. So, later on we will provide with some example just to illustrate this general equations of higher order. There is more algebra in it. Okay. So, that I just want to make remark of that. So, with this thing now we will move on to again wave equation, but now wave equation in first quadrant. So, so far we considered in the on the real line, but now we are considering only on the positive axis. Okay. So, here is the problem UTT again wave equation. Let me again just consider the homogeneous one. So, we can always use Duhamel's principle in order to get the formula for the solution of the inhomogeneous equation. So, now we consider this equation only in x positive, and as usual t is always positive. Okay. So, like the previous case, first we provide the initial conditions at time t equal to 0. As I remarked, in the case of wave equation, you can provide on any t equal to t0 line. Okay. So, there is absolutely no problem. By just translation, the solution formula can be derived. But now only x is positive. Okay. So, let me draw this domain where we are interested. So, this is the x axis and this is positive t axis. Okay. So, we are interested in this solution, finding the solution in this first quadrant x positive t positive, and now see earlier this was not there, but now there is a boundary here. Okay. So, we distinguish the initial line and the boundary line. So, let me use a different color here. A boundary. So, what is the boundary? Boundary is the t axis. So, that is x equal to 0. So, we have to provide some conditions on the boundary. So, for simplicity again let me just begin with. So, x equal to 0 now, t, I put h of t and t positive. Okay. So, such problems are referred to as initial boundary value problems. Okay. And in this case, since we are prescribing the value of the solution on the boundary, it is referred to as Dirichlet problem. There are other kinds of boundary conditions one can prescribe. So, I will mention as you go along. So, but let us now try to find the formula for this wave equation with this initial and boundary conditions. Okay. Let us try to do that. Okay. So, since most of the work is already done in the case of wave equation on the entire real line, namely D'Alembert's formula and other things. So, here it is much easier, okay, as we shall see. So, solution formula. And let us see how the boundary condition influences the formula. Okay. So, again it is very easy to explain using diagrams. Okay. So, let us, so this is the interface, there is only one point here, the origin, namely origin, which is the intersection of the initial line and the boundary line. Okay. Let us draw the characteristic here. So, they play a role here. Okay. Let me use different color here for the time being. Let me use blue. So, that is the characteristic x equal to C t passing through the origin. Why we are doing that one? Let us just see that. So, if I take any point x t here, any point x t here. So, below this characteristic, that means x is bigger than C t here and x is less than C t here. So, the geometry changes, that is what is important. And if you look at the, so again general solution of the wave equation, we already know that. Okay. So, general solution in whatever domain is of this form, f of x plus C t, there is no change here, we can use just characteristic variable and obtain this. So, f and g are two C2 function. So, again if you look at the domain of dependence property, so this value of the solution at this point is determined by the initial values in this interval, that is what is the domain of dependence. And since x is bigger than C t, this x minus C t lies on the positive axis. Thus, the value of the solution at such a point is determined only by the initial values, and because this will not see the boundary, this will not see the boundary. So, the solution is simply obtained by D'Alembert's formula. So, geometrically also we can see that. So, this the value of the solution at this point below the characteristic is not influenced by the boundary value, but situation is quite different. So, let me draw again one more picture. So, different picture. Okay. So, if I take x t here, so now remember x is less than c t. So, again if I draw the characteristics through this x t, so one characteristics intersects. See the earlier case it was not doing that. And one characteristic there is no problem. So, this x plus c t is there. Okay. So, but this characteristic does not meet the initial axis in the positive x axis, and here we do not have any data, but we have data here. Wherever it hits we pick up the value h there. So, we have to, this is okay, but how to incorporate this value to find the value of the solution at this x t. So, here we use, this is one way. So, you can again use the general solution and try to determine g, but let me use the characteristic parallelogram property to find the solution of u at this point. So, we have to construct a characteristic parallelogram. So, there are already two sides, we see that. So, this is also a characteristic and that is also a characteristic and 2 points. So, we want to find the solution there, and the data is given here. So, we also know the solution at this point, and so we need another 2 points where solution is known, but in this region we already know the solution. So, solution is known here. And that is given by the D'Alembert's formula. So, if we can choose two appropriate points in this domain, namely x bigger than c t, and which form a characteristic parallelogram, then we are able to find the solution u at the point x t. And for that, so let me just use a different color again. Okay. So, you pick a point x 0 here, x 0 small. So, we will see how small it is. X 0 is positive, small. And now you draw a characteristic okay. So, this is the characteristic. So, this you can write this x equal to x 0 plus c t. So, this one blue one is x equal to c t, that is passing through the origin, and now this is passing through the point x 0. Okay. So, that is a characteristic. Okay. So, there is now third side, and so we know the value here, because that is in the region where solution is known. So, we need one more point. So, just you draw a line, a characteristic parallel to this. So, this is one characteristic and this. So, it does not look like a parallelogram, but you can just so this is A, this is B, this is C, this is D. Okay. The solution is known at the points B, C, D. So, therefore, U A plus U C equal to U B plus U D. This is CPP, that implies U of A is equal to U of B B U of D minus U of C. Okay. So, we have to find out what is U of B and what is U of D. U of D is just very easy. So, that is the boundary data, and U of C we have to find. Okay. So, this will continue in the next class.